my background was in compilers, but I've spent 6 years at a company called Vertica, and then I worked on like an ML startup for a while now. I've worked at Influx for the last 5 years, 4.5 years, 5 years, working primarily on Arrow and DataFusion, which I'll talk about. So the goal of this particular talk, because Manos invited me, is that I want to kind of give you an exposure to what DataFusion is a little bit, but also talk about some of the technologies that are used, perhaps give you some information about what modern analytic systems are built using. And I'm going to do that by trying to explain sort of how they work. And I'm also, what I really am here to do is try to convince you to use this stuff in your research, right? And so that you can help contribute back to the different projects I'm going to talk about. That's like my real goal. So, but hopefully I'll do that in the context of teaching you something too. So the way I'm going to do this, I'll talk briefly about what DataFusion is so that you have some context, but then I'm going to spend most of the time talking about the different design decisions, but I'm going to try to use that as a way to sort of describe the different aspects of building an analytic system. And of course, then what we learned and why. So without further ado, I'll give you my pitch for what DataFusion is. So DataFusion is an open source Apache project. You can read all about it later. But if you're not familiar with LLVM, the goal, right, is a DataFusion LLVM for database. What does that mean? So if you look at what has happened over the last few years, I think the reason that there's innovation in systems programming languages, like the fact that Rust exists and Julia exists and Swift exists, is because they don't have to reinvent the whole stack from the ground up, right? You don't have to reinvent the low-level code generator and all the optimizer passes and the debugging system and all that sort of stuff. Instead, the individual systems, the languages can focus on just what makes the language special, right? Not the low-level pieces. And the LLVM is the piece that underlies those technologies, like Clang as well. So much like that, I mean, the goal in my mind for DataFusion is something similar, right? If you're building an analytics system that has to process data using columnar file formats and low-level storage and threaded, don't worry exactly what a big function library and vectorized execution and multi-thread, like all that sort of stuff. It's actually pretty well understood now because we've implemented it over the last 20 years in various different database systems. However, it's still a lot of work to implement it yourself, right? So rather than if you want to build a new database system or a data-focused analytics system, rather than to rebuild all that stuff from scratch, ideally you just use DataFusion and you can focus on that stuff that makes your application. So that's basically what it is. To give you a sense of like, not just, oh, it's a lot of work. Here's my like fun illustrative example of the kind of stuff you need to do if you're going to build a new database system. The point is not to like worry about what all this stuff means necessarily, although I suppose you're database graduate students, so you probably know most of it, right? Is that you go from like deciding you want to build a database and you have to go through a bunch of basics, like how you represent the data in memory, basic operations on it, dealing with arithmetic stuff, how you store it, whatever. And it basically takes a long time to get to the point where it even looks like a database, right? That's a lot of work. And then you'll discover all sorts of other things like the date and time expressions or how much fun joins are. It turns out both of those are like extraordinary amounts of work that like they shouldn't be really, but they are in real systems. And a whole bunch of other stuff, subqueries, outer joins. Each of these is probably worth its own like chapter in a textbook. So the point is then you get one that's pretty good. So the point is there's an awful lot of work here, right? That if you can avoid re-implementing it, probably that's good, unless it's really adding like some specific value to your system. Right? So that's like the pictorial version of why DataFusion is important, an Arrow. So you can read all about this. We had a paper in Sigmod. The website's pretty good. And I also talked about this at length on the CMU database seminar a couple of weeks ago. So that's enough about DataFusion, or at least the high level, right? So now I'm going to go into like specific design decisions and technologies that we used, and hopefully that'll be interesting. So the first thing I want to talk about is programming language. Manos suggested you guys would specifically be interested in hearing about Rust, so I'm going to give you my pitch about Rust. So when we were building DataFusion, right, this is 6 years ago approximately, the question, like one of the major decisions is what language you implemented in, right? You implemented C++, which at that point was the well-understood database implementation language. It's probably what, I don't know what you all still use, probably. I don't know. It's not a bad choice, right? But I'll explain some of the downsides. It's hard to write correct code is the main one. And then there's a bunch of stuff. So I was a professional C++ programmer for 10 years, right? So like I come from a significant amount of experience doing this. And then the second option was Rust, which the theory is it's much easier to write safe code, the theory. It was also a hip language at the time, right? Like people thought it was cool. But at that time, especially, it definitely was not. I think if you said today to people that you're going to build a database in Rust, that wouldn't be a controversial choice. But like 6 years ago, I don't think that was the case. It wasn't yet battle tested. So you can obviously guess that we picked Rust, even though we're talking about it. But I want to tell you why. Realistically, the reason DataFusion uses Rust is because the guy who started it thought Rust was cool, and this is a side project. So he just picked the one that he thought was neat, and he wanted an excuse to learn Rust, so that's why he picked it. If I'm being honest. However, there's a lot. I think turned out to have been a very good choice, and I'll explain why. So the first thing I want to foist upon you is my theory of system languages. So in particular in the 2000s, right, this is basically when I'm starting my career. C++ was the main thing that people implemented databases or other high performance systems languages in. The output speed of the binary is very, very fast, right? That's why people do it. The downside is the productivity is low. And what does productivity mean? Well, in my mind, I'll give you some personal anecdotes of where I spent time that was not productive, right? Like I spent an inordinate amount of time chasing down stupid build system nonsense, where build system nonsense means what magic WL flag do you have to put to get the linker to find the right symbol. And the other thing I spent a lot of time doing was, you put the system under load, and 3 days later, after a whole bunch of beating on it, it would crash, right? It would segfault somehow. And then the goal is like, you got to go figure out why, right? So both, like when I say productivity, it's like that kind of stuff. But the output speed was hard, so that's why people did. I think then in the 2010s, you saw a lot of people like react to that by going to Java. So major systems in this era are often written in Java. So that's like the whole Hadoop ecosystem. Spark, right? Another major system these days is written in Java. And that's people took the performance hit because the productivity is so much better. And I think the promise of Rust was basically you get most of the productivity back and the output performance is still quite good. And we can argue whether or not the last little star should be filled in or exactly how close it is, but I think the reason it's taking off and why it's a good choice is because you get a much better productivity choice compared to thing, and the output speed is quite good. It's still very good. I still think, I mean, we can argue whether it's actually as fast as C++, it's close enough. So because I wanted to illustrate this to you, let's play this fun game. So this is from some ACM paper or an article in the ACM record. I think I'm not exactly sure which one it is. But so the question is, does this program have undefined behavior? Obviously it does, right? Otherwise I wouldn't be showing it to you. But let's go. So the C++ on the left and there's Rust on the right. And I just wanted to walk through why it is and why the challenges debugging this kind of stuff in C++ is crazy. Like, I don't know how many people have already figured out the answer, but I think it's subtle, right? but it's beautifully subtle. So both of these programs create like a stack allocated heap, right? Like a dynamic sized array on the heap. That's what a CD vector is. What vec in Rust is. It's the same basic thing. Then they take a pointer to the second one, right? Like, so it's 11, right? It points to the 11. It's the second element in there. And then it adds a new element to it. And then it just prints out what was the second element. So like, what's the problem, right? Is that a memory essay? Yeah. Isn't it great?
It will resize the vector.
Almost. It might resize the vector, which is actually even worse, right? So this final thing is it might be a memory problem, but it might not be. Which is like, that's when you see people talk about undefined behavior in C, like the problem of why it's so much of a pain to find out is because sometimes it causes a problem, sometimes it doesn't. So in this case, right, as you said, if you think about what's happening here, right, there's some array somewhere on the heap, right, that has some amount of space, and you've got a pointer to it. And then this pushback in the vector, right, we'll try to add something at the end of the array. And if there's enough space in the allocation, we'll just stick it there. Everything's fine. If there's not enough space in the allocation, it will potentially copy it to somewhere else, right, that does have a big enough space and put the new one in there. So it's like only if the allocation was not big enough will it get moved. And actually, this might have probably, if you just run this program, in fact, I couldn't believe it. I actually did. Oh yeah, well, I'll get there in a second. I'll show you how it works. But it's probably like you run this, it's going to be fine. It's going to print out 12. That's even worse, right? Like you don't even see it's a problem, right? It's undefined because it's only going to crash if in the intervening time between when you did this and when the allocation happened, something else went and like refinagled the main memory. So it's probably going to look like everything's fine, right? And it will work fine until someone's really bashing on it in production. And in Rust, this will just compile error. It's the same basic thing, but instead it'll compile, it'll give you an error, and it'll complain about borrow check or something. But basically it's trying to tell you like you can't modify it while there's an outstanding pointer to something, right? You can't have both a read, you can't modify something while you have a read reference to it, is basically what will happen. So that's the core. That's why Rust is so much more productive, which I know is really simple. But In fact, I couldn't believe it. Like, so I actually went to this playground. You can go this, you try it. So you run this program, and it's exactly the same thing, and it prints out 11, right? It's fine, but it's not, right? Like, it might or might not be a memory safety problem. So again, it's so beautiful. It's a beautiful problem program. And Valgrind probably will tell you about this these days because it'll force the allocations to be right. But anyway, I spent a lot of time chasing this kind of stuff down, by the way. All right, so I also want to just give you a sense. I don't expect you to read this, but this is like what one of the inner loops of Rust, sorry, of our database implementation looks like in Rust. And I'm just trying to give you something like it basically looks kind of, in my opinion, looks like Java. It's not hard to read. Maybe that's just because I've spent a lot of time doing it, but I just wanted to point out some things. So this is basically building a specialized hash table for strings that are stored out of line, right? So they're non-individual allocations. It's very important not to like copy the strings too many times. So the first thing I wanted to point out is that just like C++, it supports generic functions, right? So basically specialized versions of this code get implemented for each one of the different particular array types, which is important if you want really specialized inner loops, which is important for performance. Again, this is like, I wanted to point out, some people will claim like because Rust has a bunch of safety, it's really hard to implement standard optimizations like short strings, right? Where instead of having short string optimization, I don't know if you're familiar with that, that's like you have a string you can represent as a pointer to like the actual string bytes, but if the string is short, you can actually stick it in the same place that the pointer goes. So I'm not going to go into how that works, but you can certainly do that with Rust. Well, I've heard people claim you can't. It's just not true. And then the other thing I wanted to point out was like, here's another piece. Most of the time, Rust doesn't deal with pointers. It will deal with offsets, right? And then to actually access memory, you basically give it a pointer to the buffer you care about, and then tell it I want this particular offset in there. And in doing that, it'll actually check the bounds, right? So at runtime, it'll generate a bounds checks, but you can turn it off, right? So that unsafe, there's like special keyword that you can turn off the bounds checkings, which you can find in performance specialized code. So like that's just trying to give you a flavor of like you kind of get the sort of not having to go chase down crazy memory problems, but it still looks reasonable. So that's my pitch. Hopefully I have convinced you now. Maybe. So yeah.
Is it practical that you're gonna do that if you have something that you really care about performance and you're gonna make sure that you as an engineer will figure out all the problems? So
absolutely.
It's on you to do that.
Yep.
But you don't want the language to worry about that. But okay.
I mean, so what this basically does, it takes a pointer and adds an offset to it and accesses memory there, right? That's what it does. Normally, if you did that in Rust would make sure that the offset you accessed it'll do some check, right? And if you don't want to do the check, you can turn off the check, but then you can absolutely go access whatever memory you want. But you have to put this magic sort of unsafe sort of like flag thing there that like highlights. Just trust me, I know what I'm doing. So yeah. So when I first started on this program, like the reason at the time I just needed a job to go back programming, right? Like I was like being a manager, and the co-founder of InfluxData was like, I need someone to help me build a column or whatever. We're gonna do it in Rust. I was like, I don't care what language, but I'm just gonna if you let me code, I'll do it. So that was basically why I picked this, right? So I didn't really know anything about Rust, and the only exposure I'd had was a couple of, I would say it was mostly people were excited about it as a technology, not particularly well, like I'd basically spent a bunch of my previous job convincing people not to add it to the stack, which is already crazy complicated. But that's a whole other story. So anyway, I thought it was hipster language, but I did it because I just needed job coding. But it turned out to be great, right? Like 4 years in, it totally lived up to the hype from my perspective. The learning curve is definitely steep, like especially if you came from C++ and you're used to doing things a certain way. Like the first 3 months of Rust was very, very frustrating because the compiler basically says, no, you can't do that, right? And you're like, I've done this for 10 years, just do it. Right? No. But once you get used to the new patterns, it's fine. And also the package manager, especially if you've like fooled around with make or CMake, I know CMake's better, but it's still pretty bad. I'm gonna be honest, especially compared to Cargo. Like these are the 3 commands you need to add like the full featured SQL engine to your project in Rust, right? One of them is going into the directory. So it's amazing to have a real product package manager. The other thing I think I didn't fully appreciate, and again, maybe this is valuable for you guys if you want to get into open source stuff, is that the fact that the compiler checks a lot of the stuff for you means that instead of relying on expert programmers to catch memory safety violations, which is what you basically have to do in the C++ project, you can rely on the compiler. And so that means that we've been able to build, like, so DataFusion is this huge open source project, right? I don't know, it's got hundreds of thousands of lines of code, but it doesn't crash, right? And part of it's because basically Rust has been doing the checks for you. So rather than have to, so I think it's basically improved our ability to like develop the project quickly, because you didn't have to spend a bunch of time chasing down memory stomps, and you don't have to wait for experts to review the code, right? Which is almost always the limiting bandwidth factor. I also think, frankly, having Rust like basically puts a barrier to entry. It actually helps filter out low quality contributions, which I think helps a lot too, for better or for worse. Yeah. All right. So hopefully that makes sense. That was my pitch about Rust. Maybe you'll perhaps do your next project in Rust. All right. So the next thing I want to talk about is memory formats. So in this particular example, you're building an analytics system. I'm talking about analytics, right? So you're not really focused on individual updates or inserts. You're focused on like calculations over large volumes of data. Modern data systems almost always use a columnar format for this these days in memory format. And so you typically would have the choice of, do you build with an existing column? Well, do you either build a specialized format? That's, I would say, the common choice, right? You build something that's specialized for your particular database, which you could basically pick off all the major systems like Spark and Velox and DuckDB. They all have some specialized array representation. Or the other alternative, which obviously we went with in DataFusion, if you picked out my thing, is Arrow, right? So there's a cross-memory, cross-platform, cross-language definition. So it's a standard way of representing arrays in memory, which sounds pretty boring. Like, there's not that many ways to represent arrays, which I'll explain in a second. But using it, it ends up constraining you to whatever Arrow can do, right? You don't have the flexibility of having your own custom format. But the upside is you get immediate ecosystem integration, right? Because lots of other systems deal with Arrow. So maybe you're better off because you don't have to do some transformation at the interface of your system, right? So maybe it's more performant, although maybe that's not that big. I don't think that's such a big deal. I think the biggest important piece here that I'll talk about is you don't have to re-implement it all yourself, right? Like, you'll hear continuing refrain here of, like, if you don't have to re-implement it yourself, obviously it's better, mostly because you can get more people to help you. Also, something else I didn't appreciate at first was if you want to provide people the ability to write user-defined functions, or if you have your own in-memory format, they basically have to write, they either have to write their functions in terms of your user-defined memory format, which could be challenging. It's a lot that goes into making a good API. Or you have to translate whatever your in-memory format is to something else that they run their UDF and then translate back, which is also not great. So obviously we went with Arrow. Part of the reason, again, was like, this is a hobby project. We were building it. So it's not like we had an army of 20 people around that could actually build this stuff. So the theory was Arrow is good enough, and we're just going to hope that it catches up. Now, I keep talking about Arrow and memory formats and stuff, and I figured maybe it would be helpful if I actually like showed what that was, because it's not rocket science, but I'll explain. So like, if you wanted to represent an Arrow, an array of 1024 8-byte integers, right? Like it's an uint array. It will not surprise you at all, right? That the way you represent this Arrow is you literally get a piece of memory that's 8,192 bytes, right? And you just put them all contiguously. It shouldn't be a shock, because this is like, if you're going to represent an array, right? There's not that many ways to represent an array of integers in memory, right? So the value of Arrow is that it standardizes how to do it. In particular, the array part maybe is obvious. How to represent nulls, right? Like, so in my example, I have null in the third element. So how do you do that? Arrow actually chooses to represent it as a validity mask. Again, this is like not rocket science. This is the kind of stuff that's in industrial systems, right? Like, for 20 years, we definitely had something like this at Vertica. But the fact that Arrow standardizes it means that now you want to pass this to some other system. You don't have to worry about, like, well, was it a null mask or was it a validity mask, right? Like, they just specify that in this case, it's a 1 where the value is not null, and it's 0 where it's null. So like, it's a very simple idea, but it actually once it's distributed throughout the ecosystem, becomes very powerful, because now you can pass these pointers around to the same memory and everyone can agree on what it means. And yes. So again, not like the actual technical details isn't like earth-shattering, but the fact that everyone uses it is. Also, for example, like, I know some of you guys are working on custom hardware, for example, right? Like, want to pick a memory format, this would be a good one because then you can immediately interoperate with a bunch of existing systems. All right. The other thing that I don't think was that I fully appreciate, this is not part of the spec, but when you build one of these analytic systems, typically the lowest level of computations are done in columnar fashion, right? They're vectorized, which is the whole reason you put them in. The whole reason you build these systems in this columnar format in the first place is so that you can do these tricks. So rather than going like one row by one row at a time, you typically will take 2 arrays at a time, and you build very, very specialized code that could do the operation really fast and take advantage specifically of modern SIMD architectures. So in this case, like the low level things, you call these compute kernels, right? In this case, it does 1 computation against 2 arrays. And so in this case, if you wanted to implement greater than, you had two numbers, right? You're trying to implement greater than. What you really want is you want something that can take advantage of the SIMD instructions, right? And compare them maybe 4 elements at a time, depending on which SIMD instructions you have and what width of the integers are, right? And you want to basically do it in blocks and then eventually sort of handle the tail, right? So like that's not earth shattering. It's basically like, it's probably CS 101 these days. The problem is there's like 50 of these things. And what you need is a big library, and then someone sit there and is obsessed about making sure this works well. Oh, it has to work with nulls, right? It has to work with all the different data types and make sure you like all that detail. So you need a library that does all that. And so actually that's a major thing that Arrow provides, our Arrow library implementation, not just the memory representation, but all these low-level compute kernels. So the primitive array ones are fairly straightforward, but there's a bunch of like string matching that is, you can imagine, it gets pretty sophisticated depending on how the strings are implemented. And so by not having to re-implement all that stuff ourselves inside DataFusion made a huge difference. Does that make sense so far? So this is kind of a potpourri of stuff that was learned. First thing was, when we first started off, all the compute kernels weren't there. So we actually spent a lot of time in the DataFusion project doing a lot of work in Arrow so that the kernels were filled out. The upside of that was that it wasn't just us, right? Arrow is used by many more systems than just DataFusion. So we had a lot of people from DataFusion contributing, but then we also had people who didn't use DataFusion also contributing stuff to Arrow, which now basically leveraged our own investment, right? We invest a little bit in, and then we get even more out. Some things that at first were, some other stuff that, especially when we originally chose, was bad. People didn't think Arrow was a good choice because Arrow was missing some pretty common optimizations in columnar databases, specifically some more of the advanced representation for run length encoding and various strings. So something called string view selection vectors. I don't know if you're familiar with that. That's like the result of a filter. You would represent it rather than copying the values around. You'd keep an extra bit mask. But it turns out Arrow basically added all that stuff subsequently. Maybe not selection vectors, but the other ones, and that's been worked out well. The other thing that if you're ever building one of these systems, it's really important that I don't think I fully appreciate is like special casing single values is really, really important, because people will write functions that have like constants in there, and you don't really want to be replicating that constant for every single row. And I guess something else that's probably way too detailed for this talk is that Arrow's type system is kind of wonky because it encodes the physical and logical type sort of both together. So like you have a dictionary array or a string array, or you can store strings in both like a dictionary or a string array or an RLE array or something else. And so the physical encoding shows up in the data type, which is kind of inconvenient. And I would have separated those more carefully early on if we'd had a chance. So anyway, that's memory. So far, so good. Now I'm going to continue to blast, and I'm going to talk about file formats, storage formats. So again, probably this is definitely a leading slide. But when you build one of these systems, you basically have a choice of, do you want your custom file format or do you use an existing file format? Like that's the high level choice. And typically, as I was mentioning, for analytic systems, you almost always have columnar file formats, right? Again, because you're focused on reading large numbers of values very quickly, not incrementally updating them. This is bad for systems that have to update things. So you use columnar file formats. And in fact, most columnar file formats that I know of do not actually store things in single columns. They actually store something, it's called in the research literature, PAX style, PAX, I believe. They're basically horizontal strips of rows, right? So you don't, if you have 1 million values in your column, you don't store all 1 million in the same column thing. You break them up into chunks, like maybe 100,000 or whatever. And then actually another very common thing is you put metadata along with each one of those horizontal strips. I believe the database literature, the first one's called zone maps. Maybe that's what Oracle called them, but it's basically metadata. And I'm obviously, like I said, I drew a leading figure here, but like you can either build your custom one, right, that has all these features and rebuild this, which is actually commonly done, right? That's what DuckDB does, what Snowflake does, but Vertica certainly had one of those. And the upside is, of course, you can get whatever specialized implementation you want. And the downside is that now it's both proprietary, like when you put data into your database, now you have to put it in the special format. So you pay a data conversion cost, which actually might be good because that actually means you have to pay a data conversion to get it out too, right? So depending if you're a vendor, that's actually probably a good thing. But maybe for users, it's not a great thing. And of course, you still have to maintain the specialized code to implement it. And the upside of using something like Parquet is that many systems can read and write it, so you don't pay the incremental conversion cost. And of course, from my software perspective, you don't have to re-implement the same thing again and again, right? You don't have to maintain that code by yourself. So what we did, we obviously went with the standard file formats. We picked a bunch of them. I'm going to talk a lot about Parquet, but we also support these other basically open source standard stuff. And the other thing that I want to start talking about is we also support extension APIs for everything. So DataFusion has a bunch of features, right? But it's also been designed so that all the APIs that are important, you can substitute your own implementations in for. So like the way we've implemented the Parquet reader uses the same exact API as you would use for implementing your own custom file format. So like if you wanted to test out or do research, for example, intent on custom file formats or reading from specialized hardware or something, you just follow the same API, which is in terms of Arrow, right? And it pushes the predicates and stuff down for you. And the theory was that Parquet, the file format was good enough, lots of current discussion notwithstanding, that you'd be able to, with like enough engineering effort, you'd be able to make the thing really fast. And of course, the fact that there's a huge amount of Parquet files out there already means if you could do it really quickly, you get a lot of leverage. So again, since I figured I have no idea how much any of you know about Parquet or not, I figured I'd try to like explain a little bit of how it worked, just to give you like some, like, so you like learn something maybe from the talk, not just me talking about some system you don't know about or care about. So the way Parquet is implemented, the horizontal strips are called row groups in Parquet, and the individual columns are called column chunks. And so the way Parquet is organized logically is like this. So in this case, if I had a table, right, that had 3 columns and had a bunch of rows, what you'd actually do is you'd take column A and you'd break it into, you'd take it into 2 horizontal, you break the data into 2 horizontal strips, right? Like, and then each one of those you'd encode. So like the first however many rows would go in column chunk A, B, and C. Right? So you break it up into 6 individual pieces. Does that make sense? And you know, there's blogs and stuff. You can read all about this if you want. And then the second rows would go in there. And I think, and then if you look at how the data, the actual file is structured, each one of those column chunks, it's actually broken down into a lower level thing called data pages, but at a high level, it encodes each one of the columns as individual data pages, writes those somewhere in the file, and then writes a footer at the end of the file that has information about each one of those row groups and data pages and how to find them and stuff. And so then when you get the footer has this information like min-max values for each one of the columns in the column chunks. Yes, and that's the zone map small materials aggregate thing, right? So then what happens, what's actually really cool in the query processing is that you use that metadata in the footer to only pick the pages that could possibly match. Right? So like in most of analytic systems, the name of the game for performance is you just like filter the data as fast as you possibly can, right? So you're trying to do as little work as possible. And so this is one of the major techniques you would use for filtering out storage, right? You just skip a whole bunch of work you have to do. So if you had a query that was like this, right, you're selecting A where C is greater than 25, what the query engine would do, and what DataFusion does, right, not everything else that uses this type of format, is you read the metadata footer, which has minimum and maximum values for all the columns, including C. Right, and then you could use that information to figure out quickly which one of the data pages you need to read. Right, like if you knew the maximum value in C was, the maximum value in C was like 10, right? You know, in a certain horizontal strip and a horizontal row group, you know, you don't have to look at any of that data. And like with a couple of quick comparisons, you can skip hundreds of thousands of rows. Likewise, the fact that I know I'm only scanning, I only care about the values in column A means I don't have to look at anything related to column B. So like I have a whole series of pages I don't have to even look at. Does that make sense? Yeah. So that's like the high level row group pruning with Parquet. I'm describing this in the Parquet terms, but this is basically when people use small materials aggregates and packs, like that's what it's doing. So it's not, I mean, in some ways it's not that complicated, but actually making this work across any arbitrary predicate, right, is a non-trivial endeavor. Okay. Oh, and all the crazy different data types and the 15 different kinds of timestamps or whatever. Yes. So I think the lessons learned I had from this particular endeavor was using the standard format definitely constrained us to like what Parquet could do. And you can read lots of blogs on the internet about limitations in Parquet and various ways people would change it if they weren't constrained there. But I think the original theory was it's good enough. And actually the existing software implementation had lots more optimization opportunities. And so we actually spent like a significant chunk of the last 4 years I'm very biased, right? You got to make sure you understand I'm coming at it from an angle. Like we spent a lot of time making the Parquet reader very fast and integrating it well in DataFusion. And so like actually pruning all the row groups, it works really well. And it doesn't copy stuff and it interleaves the IO and it does a whole bunch of work optimizations that was required to even take advantage of what was in Parquet. Right before I think we should even start talking about like, well, how should we fix Parquet, right? For example, people talk about changing the file format metadata, the footer metadata because so anyway, the point is there's a lot more benefit. Like if you guys want a fun project, you can go make the C++1 probably 4 times faster if you wanted. The Rust one's pretty fast. Anyway, the other thing too, again, that's cool about working on these open formats with the open source implementation is that it's not just us, right? It's not just the people, it's not just Influx, it's not just the people who care about DataFusion. There's a whole bunch of other people who've actually contributed significantly to the Parquet implementation. And part of it is you got to provide code. Part of it is, you run around and do talks like this or talk to various people to convince them. But a good example is actually one of our interns this summer was, he's a student at University of Wisconsin-Madison, and he's basically working on like low-level late materialization and the Parquet predicate filtering stuff is a thing. So that's another example where he's doing research work, but he's going to do it in the context of an industrial system. I think we'll get some good stuff out of that. And he'll hopefully get a good research paper out of it. You could do it too, maybe. Anyway, yeah. So that's that. I know I'm going on for a while. I have a lot more slides, so I'll probably not go through all of them, but I'll talk through a couple other major pieces that I think are important. So the next thing is a catalog, right? Do you know what what is a catalog? It's a catalog in a database system is basically the information, I'm talking about, you have the file and it does this thing. Like, how do you know what files exist that make your database? How do you know what tables there exist, what the schemas are, who has access to them, all that sort of stuff? That's typically called a catalog, right? You probably know from Database 101. And so there's like when you're building your database system, you typically have two options, or at least there's at least two options. The first is you provide your own catalog implementation. For example, like DuckDB or SQLite do this. There's just some file format that has all the information the database needs to find its data and add stuff to it. And the upside of that is like the system just works out of the box. You don't have to worry about formats or whatever. And that's good. The downside is it's very bound to the particular case. Like, for example, if you pick a local file as your catalog implementation, it's great if you have a local file system. But if you're trying to build like a cloud system, it's not so great, right? Because now you got to have it just, how do you have all the machines agree on what the version of the catalog is? And likewise, if you build some complicated distributed catalog, now it's not great if all you just want to do is fire it up locally and run. And so the other option that I've seen people do is like you build an API, right? Like that's the obvious thing to do so that the users can plug in whatever implementation works best for them. So if you need a remote catalog, you build that. If you need a local file system, you build that. And the downside of doing that approach, of course, is that now to actually even start using the project at all, you have to provide a catalog implementation, right? Which isn't necessarily good. So that's actually what like Calcite does. If you're familiar with Calcite, that's an open source SQL planner. Which, maybe you never had to do that, but if you want to use it, if you want to plan SQL queries without actually having to worry about its implementation, you can use something like Calcite. The downside is to actually get it to work at first, you have to basically give it the information in the format that it wants. So what we actually did, which worked out far better than I ever could have imagined, actually, is you provide two really simple implementations and then provide the API to extend it whether people want. So in particular, we in DataFusion provided two specific implementations. There's like an ephemeral in-memory one, right? That as soon as you quit the process, it all goes away, which is great for testing. And then there's another one that grandiosely is called file-based Hive partitioning, blah, blah, blah. But what it really means is it's a directory full of files, which actually, sounds ridiculous, but a lot of people have directories full of files and it's super widely used. And then we have an API for basically every other system. So we have, and that pattern of simple stuff that's good enough to get working along with an API that people can use to extend permeates throughout DataFusion, and it's been super, super valuable, I think, because people can start quickly and then pick where and all this giant feature set, right? You pick the ones that you care about extending and you can work on the rest. Like, for example, if you have some research project, you don't want to build a whole database system, right? If you only want to change one little thing, this would be a good way to do it. So yeah, and the reason, by the way, is to not pick something more complicated to include is because anything you pick is probably not going to work for a large variety of use cases, right? Like pick some, what remote file format, maybe it's a Postgres one, maybe it's a Redis one, maybe it's a who knows what, it's probably not going to work in a lot of different systems. File-based ones do. So speaking of file-based ones, this is probably horrifying to you guys as database researchers, but I'll tell you what's super common in the real world is directories full of files, right? And so there's definitely just the directory full of files here in the top left, right, where there's table one, it's got two Parquet files in it. So DataFusion and many other systems will just treat that like a single table. You can select star from table and it will look at those two files, merge the schemas and present it to you as a single table. There's actually a subsequent refinement of that, which again is horrifying, but actually shows up in the real world, is that there won't just be a single directory, it's full of subdirectories. And the subdirectory is actually literally named date equals whatever, that's the name of the subdirectory. And so what will happen, what the meaning of that structure is that we'll have all the columns that are in the Parquet file, and then we'll actually add it'll add another sort of synthetic column called date in this case, right? When the date for the file 3 and 4 is the June 1st, 6/1, and then the date column values for all the values in file 5 is the next one. And then, so this is called Hive style partitioning. And so what systems will do is then if you have a predicate on the date, you'll have very simple partition pruning of this, right? You'll actually be able to, if you have a predicate that says, I only want the values where it's in June 2nd, it'll actually quickly go and skip a whole bunch of files.
Just understand something, because you mentioned that the schema is predefined, right? It's not defined by just reading the files.
No, it is defined by reading the file.
Oh, it is defined by reading.
Yes.
Yes. And this is for example, in the general in DataFusion approach, that's how it would work, or yeah, okay. Okay.
Yes. And again, DataFusion did not invent this, right? This is
right.
This is very common. I think this largely came out of the Hadoop ecosystem.
Okay.
The benefit of this scheme, by the way, is that you don't have to have a separate catalog, right? That you can just use the contents of the file system and interpret that directly as the data.
So what happens at create data statement? I mean, you don't store anything other than whatever structure you decide to do in your files?
So if you wanted to read this, for example, you'd say create whatever the table was and give it the path of how to find it.
Read it from there. Obviously.
And Parquet is a nice file format because embedded in the file itself, it actually has the schema of the data, right? So it has the type schema. It's not like CSV file. Well, it'll work. You can do this with CSV files too.
Right, but not being fast.
Then you have to infer which DataFusion will do and other systems will do, but it's more error prone. And there's a whole bunch of other subtleties here, right? Well, what if not all the columns are in all the files, right? What do you do, right? Or what happens if the columns are different data types? And the answer is one, you fill in the first one with null. The answer to the second one is you throw an error. So is basically what happens.
So this allows for a lot of liberty, a lot of
Oh yes. Yeah. Yeah. I mean, if you look at I don't know about the vast majority, but a huge amount of data in real world systems is basically stored like this. And if you've heard about systems like Iceberg or Hootie or Delta RS, what there is that fundamentally the data is still stored this way, but then they add a second level of metadata on top of it that let you do things like like in this case, if you wanted snapshot isolation, right? Like what's the current content of the table? Well, you got to look at whatever's in the directory and hope, that's the current content. If you wanted to like add in a transactional style data to both two tables, for example, there's no way to do that if you have just file systems. So, or if you want to delete stuff, God help you, right? Or rewrite it, right? Like there's no way to represent that in this structure. So that's the kind of feature that those catalog formats add. But at the end of the day, there's directory full of files. No. Okay. So some of the stuff I guess we learned here was, again, like creating these basic implementations worked great. Something else that I certainly didn't appreciate is the actual amount of code that goes into making this work is actually this being the directory full of files and making it work right. And dealing with all the stuff we actually were just talking about is actually far more complicated than I originally realized. But so it would have been nice to have like a cleaner separation, but that's worked out well, far better than I would have expected. And again, like, that's not something we're making up. It's just something that kind of emerged. All right, so now for the last like 10 minutes, I will regale you with stories about SQL planning and SQL dialects, if I can, and then it'll be time for lunch. So, all right, another question you have when you're implementing one of these systems, right, is what SQL dialect do you pick? And first of all, someone might say, well, the obvious answer is you use standard ANSI SQL, and there's no such thing. I don't care what people say. Yes, there's like a 1,600-page spec somewhere that claims to be ANSI SQL, but I challenge you to read that and actually figure out what it means and or map it to figure out like, does this particular implementation actually match the ANSI? Like it's, I don't know who wrote that or why they think it's a spec, but it's not. So anyway, if someone says that they implement ANSI SQL, they're lying or they don't understand what they're talking about. What actually happens in the real world is there's a common core of SQL that gets implemented over and over again. And then people add, the different implementations have different dialects. And so the dialects are slight subtleties about both syntax and then the semantics of how things work. And so when you're building your system, you typically have the choice of like, well, you pick some existing dialect and try to make it bug for bug compatible, or do you make you just try to pick an existing one. So good side about picking your own SQL dialect, like this, what DuckDB did. You can basically try to improve SQL all the different ways that you don't like about it. You can fix them with your own dialect, but you also make the problem worse because now you made a new dialect. Or you can go with an existing dialect, which has all the problems that you know about, but at least you don't have to infer it. And the big thing is you don't have to invent the new semantics, right?
You also go and work with the ANSI committee to change them.
You can try to work with the ANSI committee to add stuff to it.
It's actually a slow process, but people are, I think, doing that. So.
People do it. It's probably worth a whole separate talk about.
Right.
So one of the things I do is I help maintain the SQL parser implementation in Rust, and it has support for like 10 different dialects, like Redshift, subquery, like Snowflake. It turns out, like, in seeing the distinctions that people have to add to support the different dialects, like it's just crazy the differences. Like BigQuery, I believe, at least was like the worst, at least recently, about like adding random syntax. Well, not adding random, sorry, having syntax that only worked in BigQuery that was like slightly different than everyone else. And I'm just talking syntax, right? We haven't talked about semantics yet. So yeah, you can probably guess, right? I'm leading to the answer. What we did is we picked an existing one. We picked Postgres. It was good because we didn't, like, it's well understood. It's like had 20 years of study, right? You don't have to spend a lot of time defining the semantics. The downside, of course, is that not everyone likes Postgres, right? Some people want their system to behave like Spark, or some people want their system to behave like something else. It also turns out that the syntax is actually only a part of what it takes to implement the dialect. Arguably a much larger piece is the semantics of all the functions. Like stupid stuff, like if you put invalid arguments into a function, does it error or does it return null? Like it depends is the real answer on the different dialects. So again, like that's the kind of stuff that not having to define saves you a lot of time, but it's hard to get right. It also turns out data types, again, like it's supposed to be a SQL standard data types, like it's just not true, right? Like there's something called varchar2 in Oracle. Like some systems support char, sometimes they support varchar, sometimes they're size, sometimes they're not, right? Like, and I'm being glib about this, but like it's a real problem. What's the actual data type of a timestamp? Does it have a time zone? And then what happens if you try to call a function that takes an integer, but you give it a string, right? Like, different databases have different answers. But I don't know. So it's not like ideal, but on the whole, this is a lot better than inventing a new dialect, in my opinion. And we also tried again to like give people the ability, if they wanted some different dialect with different functions, you can go plug in your own implementations rather than just be stuck with what we have. Another thing you have to figure out is planning. Planning is the process of going from like a text string, right? That's how you actually type SQL, right? It's a text string. And it comes eventually to a plan, which is a description of the data flow graph. And so the question is, do you write your own translation of text string to data flow graph, or do you use an existing planner? The only one I actually really know about that's plausible was Calcite at the time. So this is this like, it's what Spark uses, and there's a couple other major components in the Java Hadoop ecosystem that basically standardized on one SQL planner. The downside of Calcite was that it was in Java is the major problem. The subsequent problem is also that the representation of the query and the representation of the plan, right? It's like some Calcite specific things. So you have to map back to whatever your system does. We did our own planner. It's a huge amount of complexity. I'm not sure, like if you could avoid this, building your own system, it would be great. But we couldn't figure out how to do it. So it's very nice now. It's a pure Rust stack. It's very easy to integrate DataFusion with stuff, like embed it. But the SQL planner is a lot of work.
Is plan based optimization tool?
Well, this is the planner. There are optimization steps that happen typically on the logical plan representation, which I could talk about. Like there's a lot of them. Yes, that's like a big chunk of the DataFusion talk. I could talk all about that. But this is just literally the translation from the SQL string to a plan that calculates the answer that was desired. Yes. So yeah, it was a lot of work. That's basically the conclusion. And so if you can avoid doing this, I would very much recommend it. It's a lot of work. Plan representation. Maybe I'll talk very briefly about this stuff. This is like, if you've got a database system, right? Any databases, you're going to end up representing the actual query plans as a data flow graph, right? So it's basically representing data flowing from data sources, and then different systems have different structures, but they all basically represent data flowing from data sources up through and eventually getting to where the data is going. And so the question is, how do you actually represent that plan? It's not just the nodes in the graph, it's also how you represent the expressions internally. And so again, the typical choices are you build something entirely custom, right? Or you use an existing library. In this case, I think the obvious existing library is something called Substrate. But what we actually ended up doing was building our own. DataFusion built its own. I think realistically, the reason we did that is because at this point, there was no compelling alternative. Like there just wasn't, like Substrate existed, I think well, DataFusion started, I'm not sure Substrate existed. But now if you're going to build a system, I would recommend using Substrate for all the same reasons I basically talked about for Arrow RS, which is not that all the existing Substrate implementations are going to be great, but like if you work with the people and make those better, I think you'd have that would be a much better time than trying to do it all yourself. Part of the reason is just like, it's like just a huge amount of code that's not particularly, like it doesn't really add value, right? Like it's basically like tree walking code, right? How do you how do you write the trees? How do you rewrite them? And so it's a lot of API design work and implementation that's not particularly value added to the overall project. Also, really, like there's a bunch of practical things that are very important, like how do you serialize these plans into some format that you can send over the network and turn back into structures on the other end? Again, like it's like CS 101 kind of stuff, but it takes a lot of like actual code to make and to maintain it. So not having to do that is I would recommend it, which we weren't able to pull off. Here's something Manos was hinting at. You can have a very complicated optimizer. I'm not going to talk about this at all because I'm almost out of time. But basically, in the context of a database system, there's a bunch of optimizations you could do. The hardest one, as you probably know as database researchers, is join ordering, right? You can get a query that has a bunch of joins in it, and then the actual order that you do the joins can make orders of magnitude difference. This is like, I spent a huge amount of my time. I'm pretty sure I did a PhD on this. I'm sure there's lots of other people doing PhDs. There's always papers about how to try to do this better. And basically, the high level, what almost all systems do, if I can like wave away all the important details, is they basically have some sort of heuristics that pick a subset of the search space to look at, and then they have a cost model that picks which one of the enumerations they do. And getting that cost model right is basically impossible, is my personal opinion. Like getting it working right for real in all cases is basically impossible. Or no, that's not true. It's an unsolved research problem. So, which people keep trying to solve, but it's not solved yet. And then his other option is basically just be really simple, right? I love it. There's a quote from Andy Pavlo's CMU lectures about like, Oracle introduced like the syntactic optimizer, which makes it sound very fancy, but what that really means is you just do the joins in the order that the person typed it in, right? Which is very simple, very easy to understand, but of course it's very easy for them to get it wrong, especially when it gets complicated. And so we basically went with syntactic optimizer because it's simple, and I'd been like basically suffering from PTSD. So I worked at a company called Vertica for 6 years, and like I spent a big chunk of that time working on the join order, like the optimizer and the join order enumeration stuff. It's very, very hard to get it working great. So we don't have anything like that complicated in DataFusion. Instead, we have syntactic optimizer, but give you just enough to avoid TPCH disasters, as you probably know from writing papers, right? You can't have really crappy TPCH results. So, we have something basic, and eventually, like you can actually see we had a TPCH disaster in our Sigma paper, and it's because like the costing of subquery cardinality, blah blah blah, wasn't quite right, which we subsequently fixed, but I think it's a good example of that. So anyway, with that being said, my conclusion is that analytic systems are a huge amount of work. Using existing software is much better, obviously, but I think realistically now there's like pieces of analytic technology that are mature enough that people are using, because it's like the third time we've gone through and implemented them in industrial systems, that they're good and you can actually reuse them. And of course, I think also the idea of, if you're going to build a system, having something that's basic that people will start with quickly, but then also have APIs to let them customize it, has been super, super valuable. Yes, so that's it. I would love it if you can help us. Thank you. You don't know. Yes, sir. We have a couple minutes for questions, but I know I talked for a long time, so.